This second leg of the prospecting session. I'm Dennis Harries, I'm at ESRIC, and in this session we are going to hear about measurements and instruments. So we have a very interesting mix of missions, analytical instruments, and actual analysis done on samples. And I'm very pleased that in the end we also have Antonino Salmeri, who is going to talk about the aspects of data sharing in a world where we have both public and private entities working on generating planetary data. So with no further ado, I'd like to welcome Fabrizio Fiore on the stage, talking about the PRORIS-HARLOC project for moon resource prospecting. It's yours.
Okay, thank you. I would like to introduce you to this project for prospecting of resources on the moon using instrumentation on rovers. The motivation, I should not spend much words about this because this was discussed at length this morning. Basically, we want to pass from scientific investigation to resource utilization. And the point is that to do this, we really need to have, as we heard this morning, we really need to have information on spatial scales as small as possible, down to meters or 10 meters. So what is this project? This is a 3-year project that is funded by the Italian Ministry for University and Research through INAF and CNR. And we have two main goals. First is about ice water, because we want to understand which are the physical conditions in which ice water is found on the moon, whether it is found in hydrated minerals or in small ice granules mixed with the regolith. And we want to understand which is the distribution on scales of meters. The second goal is to investigate precious minerals like rare earth elements, or as we heard this morning or yesterday, helium-3 associated to titanium. The point is to understand whether on the moon there are ore deposits. Here in this plot you can see the situation as of today, in which there is a comparison of what we have on Earth about rare earths ores and what is assumed to be on the moon. Of course, the situation here is very uncertain, and what we would like to do is to reduce these uncertainties. So the project is divided in two. There are instruments on which we are aiming at have TRL9 in 3 years, and instruments that are based on adapting what was done on Earth, that are aimed to have TRL in 4 to 5 in 3 years. So about ice water, the main scientific target is to focus on ice deposit at the poles, where we studied the geomorphological context, the thermal condition, and the accessibility that, as we also heard this morning, is very important. The instruments that we are studying are ground-penetrating radar, electrical resistivity instruments, passive seismology, and microwave radiometers. Here the point is to have an informed assessment of observational requirement to reduce the risk. About the rare earths, Here, what we want to do is to focus on Cripps terrain and determining which tracers are best to use. Of course, we know that we can use thorium or samarium maps, but also silicon anomalies, but everything should be put in a context, in a geomorphological context, because of course the most probable sites for rare earths ores are outcrops. Here the added value is really have a link between the orbital scale, the geomorphological context, and in situ measurements. And we are doing this using a suite of instruments that I will describe in the following. So what we want to do is, as I said, to bridge the gap from the information that we have from remote sensing and what we really want to have that is on scales of tens of meters. Here you can see what has been assessed in the past. For example, the fact that on the moon there are silicic non-mare volcanic constructs that are probably very rich in thorium and very rich in rare earths. And here you see an example, the Aristarchus crater, for which there have been evidence of a thorium overabundance, but also of a silicon anomaly. And this is a plot of the so-called Christiansen feature observed by the Diviner instrument. Point is that the thorium scale is huge, 40 kilometers, but also the Diviner data are on scales of 200 meters. Each resolution point in this plot is 200 meters. And you can see what is 200 meters on the lunar surface. It's really a huge area in which, of course, it is very important to understand from where this excess of emission is coming. And here it is another example of a red spot, the Einstein Alpha site, for which there was a detection of a large thorium excess that is in coincidence with an anomalous value of the iron concentration. And this is an overplot of the Diviner data that show that exactly in that site there is a silicon overabundance. But again, the Diviner data has a spatial resolution of up to 200 meters. So, which is our approach? Our approach is to basically try to make high resolution, precise prospecting using instrumentation that was developed in the past for scientific purpose. The reason is that this scientific instrumentation was developed to follow tight scientific requirements to have high-level performance. The other point is that this instrumentation was already developed and flown, so it has very high TRL, and therefore we can have a very quick repurposing time. And even most important, the fact that it was developed by very experienced teams. And I stress that there are several posters that describe this instrumentation. So this is our CONOPS, our approach, which is in a sense the new part of the project. We will use first a gamma ray payload to map thorium on scales of tens or hundreds of meters using this instrument on a rover. When we find an excess of thorium emission, we drive the rover toward that direction, and we start to use the other instrumentation, that is Shy4D, that is a multispectral stereo camera that can give us information on scales of meters to centimeters. Then, when we find interesting spots, we use instrumentation that can analyze these spots on scales of centimeters. A rescue, that is a UV, that is to do maps of fluorescent UV emission, and finally an XRF instrument that can give us information of abundances on scales smaller than 1 centimeter. So the approach is really to bridge the gap between large scales, hundreds of meters, to very small scales, a centimeter. Everything is assisted by an AI module that is able to analyze the data on the fly. And in fact, this is a very important feature of our project, because we want to have an autonomous mission control, reduce the dependence on air control, and the possibility to do data fusion on the fly. So this is a summary of this project that is based on 3 pillars. First, the goal of bridging the gap between remote sensing observations and the information that can be brought on the moon on very small scales. The second is to reach this goal by adapting instrumentation developed for scientific purpose and use on board AI-driven data fusion for autonomous operation. Thanks a lot for your attention.
Thank you, Fabrizio. Are there questions? Clive, you were the fastest.
Yeah, thank you very much. A very interesting talk. I'm intrigued, you're mounting a gamma ray spectrometer on a rover. How fast can you rove and still get good data?
So the idea is to use the gamma ray spectrometer with integration times of, let's say, 5 to 10 minutes at each single position to make observations around moving the rover and understanding in which position there is an excess of thorium emission.
Okay, thank you.
Ben, please.
Ben Bussey, Intuitive Machines, now having to pick a different question. I didn't see the mass and power for Harlock that the rover would have to support.
Can you put...
Yeah, sorry. I didn't see what your mass and power requirement for Harlock was.
So he asked about the mass and power requirements.
Okay. Each instrument is tiny, is the order of 1 to 2 kilograms, and power requirements are also tiny, the order of a few watts per instrument.
Any other quick question?
I've just got a quick question. I was wondering, given that you're prospecting for rare earth elements, is there an assumption that you'll be able to extract it fairly easily? Because obviously on Earth, it's extremely difficult to extract rare earth elements. So it's quite a significant assumption that we can actually extract them.
Yeah, of course, this is a very important point. Our goal is only to do prospecting and assessment of resources. What I know is that there are startups, in particular in the US, that are addressing the problem of extracting rare earths directly on the moon. Actually, there are a couple of projects that are funded by NASA, and I understand that they reached also quite an ITRL this year. So there is something ongoing on this respect. But of course, this is an important point to be addressed.
Thank you.
So, thank you again, Fabrizio. Another applause, please. And it's now my pleasure to welcome on the stage Jakub Ciążela. I hope I pronounced it correctly.
I know this is challenging for Germans. I spent 5 years in Germany, but that was very good, actually. I'm happy to be here, third time in a row. Last year, representing this institute. Actually, 2 years ago, last year, I represented the company. And this year, company Mirrorless. And this year, I represent both to talk about new ESA mission that is scheduled for 2029. And we are currently in phase 2 of preparation. So in our nomenclature, this is phase A and phase B1 combined together. And this mission will focus on resources because, of course, ESA needs them too. To construct lunar bases, the market is growing every year, and ESA supports many projects currently concerning resources. And even here, if you can see, I calculated today that about 93% of talks concern the moon, Mars, just 7%. Last year it was even worse. Also Elon Musk comes back to the moon now, not to Mars anymore. So all forces are focused on the moon, and this is one of side projects that we also do funded by ESA. This is a map of resources, so a database of all geological map we have from the moon, and on top of that, addition from us, maps of resource probabilities, resource potential indices. This is a database which is almost available right now. We are making final steps. You can see what you can do. You can, of course, zoom in, zoom out. You have different projection modes, including global and polar projections, and also different layers, of course. You can switch between the layers. You can make some operations. And this is a finished project available very soon. This week, or actually next week, we are kicking off with the new project in Aztec, which will be based on that previous one. But in this project, we will help in building the lunar economy based on resources that we've already mapped. So far, we know that we have different resources that we need to cover. And water, of course, you know, it's in polar regions only. But it can be surprise, or maybe not for this community, but this is the fact that the other resources are in another place, mostly in lunar Maria, so in these dark areas of the moon. And most of metal data, this is very clear. We have iron and also titanium content, which is clearly related to lunar Maria. This is, of course, due to ilmenite content in this basalt. So ilmenite is iron, titanium oxide. And because it is an oxide, you have oxygen as well, which is a propellant. And I saw Clive talk saying maybe this is not so easy to extract oxygen from there yet, but this is probably the best we can do. And there is an entire session about that. But ilmenite, except for oxygen and metals, have a third resource, which is energy resource, which you also know very well from previous talks. And this is helium-3, simply because you don't have magnetosphere and an atmosphere on the moon. So moon collects helium-3 much more effectively than Earth. And it was also discussed during Clive talk that it correlates with this parameter related to titanium content, maturity and solar flux. This is Apollo-based correlation, so this is quite robust, and we can assume that where we have titanium, we also have helium-3. This is an old map. Recently, we did a new one. This is my master's student who helped a new map of helium-3 also in our repository available for you. And why is this energy resources? Because of thermonuclear fusion, and it's better for some reasons. I took this figure from Abigail, modified slightly. It's better for some reasons because it doesn't emit neutrons, just protons, so they go into atmosphere because protons are essentially hydrogen, but it requires higher temperatures, not 70 million kelvins, but 300, 400 million kelvins. And currently, we are at 70 million kelvins, and only for 17 minutes. This is achieved by Chinese a few years ago. We are close to France, and France beaten this record to 22 minutes, but you see the progress is not very high. It's not something that we'll achieve very quickly, and ITER construction is already lasting more than 2 decades, and it will last still 15 years. So I think thermonuclear fusion won't be the first application we'll have for helium-3 and for the market price of $20 million. The first application will be probably quantum computing, and this is what contracts are made for, including Interloon that was presenting here yesterday. So this might happen, but we need more geological prospecting. Ilmenite, the gray mineral, is associated with sulfides, and this is good because, and actually this is a picture from Earth, but if you analyze pictures from Mars, from meteorites, also Apollo data, sulfur correlates with titanium, so sulfide occurrence correlates with ilmenite. And this is good because oxides contain siderophile elements, sulfides contain chalcophile elements, so if you combine together, you have half of periodic table. And there is another good news that rare earth elements discussed today occur roughly in the same areas of the moon, in the creep areas, which are more or less associated with lunar maria. This is, of course, large-scale map using thorium as a proxy that was explained in previous talks. On Earth, we use, this is a study of my PhD student, we use spectra, including infrared, but as was discussed today, it's difficult on the moon because we don't have much of these minerals like bastnasite. However, we have apatite, and apatite can be detected well in a spectrum in which we will operate far infrared and mid-infrared spectroscopy. Coming back to sulfides, they are important for solar energy. I know there are colleagues from Caltech, Catherine, among the viewers who do that. There is also another application for constructions. Sulfur will be used instead of water for lunar concrete because it's more abundant than water. Data, including Chandrayaan, but also Apollo data, suggest we have a consistent 1,000 ppm of sulfur in many areas on the moon. So that's why this mission I want to talk about, to detect all these resources. So MIRROR-S is the payload selected for that for one reason. It is a first payload that will operate in far infrared spectrum of infrared. So this gives an advantage. There were no missions operating in this range so far. And it gives advantage because of two reasons. In near-infrared, spectra of sulfides are too flat and also too similar to abundant pyroxenes, so impossible, nearly impossible to detect. In far infrared, they give excellent spectral features and much better than silicates, actually, in the top right corner. So if you make simulation, even having 10 or 20% pyrite, you can detect it from the orbit. This is how it looks like. The spectrometer is called mirrorless because it's composed of two mirrors, except for that the name is multiplanetary infrared or spectroscopy or spectrometer. So this is also an acronym. Here you can see it better. There are two mirrors, secondary mirror on the top and primary mirror. And then in front of each detector, you have collimator to protect us from stray light. Detectors were already tested in the lab. This is a study of Sumit Goski, present here as well, my former master student. We've demonstrated we are capable to detect sulfides in this far infrared range. And we've also constructed prototype that is operating. It was also presented in Geneva at the ESA stand last year at the exhibition of inventions. And it was tested extensively in the field, in different mines, in Sierra Gorda, in Chile, also in Rio Tinto in Spain with pyrite mineralization. And it achieved ESA Technology Transfer Award for that because it's of interest for mines as well. It operates not only in this vertical position, but also in horizontal position, as it will be presented on this movie here. And that's why it's interesting for mines, because mines needs also to investigate outcrops except for prospecting. On Earth, it's possible to use on drones because it's not blocked, because altitude is low enough. A lot of signal is lost, but not all. But from satellites, we cannot see anything in this spectral range. However, on the moon, situation is perfect as there is no atmosphere. Even on Mars, we have some water in the atmosphere, but on moon, no water. And that's why this spectrometer, originally developed for Mars, was adapted to the moon, and now we put all forces to send it to the moon in 2029. Thank you very much for your attention, and welcome questions.
Thank you, Jakub, for this very detailed talk. We have a little bit of time for a very quick question and a very quick answer. Is there anyone? Ruby.
Hi, my name is Ruby Patterson. When you deployed this and ground truthed the data in the mines, did you deploy it on a drone, or was that also done from orbit?
So for the mines, we can only deploy it from the drone because water vapor blocks all signal from the orbit. You can only operate on a short column below 100 meters to see signal clearly enough. Thank you.
Thank you, Jakub. So for the sake of timekeeping, we have to move on.
Thank you. Thank you very much.
Jakub, the mic, please. So our next speaker is going to be Lisa Krämer Ruggiu. I'm sorry.
Thank you. It's fine.
Okay. That's really the hard part of convening.
Yeah, I'm sorry. This is not an easy one.
And it's going to be about a topic that's very dear to me. It's about meteorites and how we can use meteorites as laboratory analogs for the actual materials we want to study in space.
Hello, everyone. So my name is Lisa. Let's keep it short. And today I'll keep you a little bit away from the moon for a few minutes, and I'll talk a little bit more about asteroids and meteorites. So I work in Brussels at a university as a postdoctoral fellow, but this work has also been done with my students, so Zibresh has done a lot of the work here, so I'll try to present it as thoroughly as possible. So we know that we have over 73 million meteorites in our labs as of today, maybe more, and more than 1 million asteroids in the solar system. We also have meteorites coming from the moon and from Mars, which have had very nice presentations today. But to understand everything that's been measured in a lab, because planetary scientists like to measure a lot of data on meteorites, we need to know exactly where they come from to put all the data back in the context of the solar system. But also to understand the surfaces of those asteroids for space resources, but also for any kind of data management and data understanding. So knowing where those meteorites come from is actually not that simple. And to do that, one of the tools that we can use is infrared reflectance spectroscopy. It's supposed to be there. And I'll try today to show you a little bit how we use infrared reflectance spectroscopy on meteorites and how those meteorites can actually be extremely useful for space missions. So a small reminder of infrared reflectance spectroscopy. So we basically measure the light reflected back from the surfaces of asteroids using the VLTs in Chile, for example. And thus we extract infrared reflectance spectra, which is one of the examples you see here. And basically the importance to check on the spectra is the shape of the spectra. We have absorption bands, so small dips in the spectra at 1 and 2 microns. And those are important because those are the basics of how we classify the different families of asteroids. Today, I will not show you all the families, of course. I will focus on the S complex, so the silicate-rich material. Why the S complex? Because of the Hera mission. So the Hera mission is the one coming after the DART mission with the impact, and it's been studying Dimorphos and Didymos binary systems. And this binary system is actually a S-type asteroid binary system, so it's silicate-rich material. The Hera mission is trying to understand the mass of Dimorphos, the crater formation from the DART, and also the asteroid surface and the interior of the asteroids. Which is where the Hera mission came to me and asked me if I could find a meteorite analog in our lab that we have already, as close as possible to the actual surface of the asteroids, for many reasons that I'll explain a little bit later. So of course, I had to measure lots of meteorites. And how do we measure those? So we try to mimic, as well as possible, what's been measured with the large telescopes. For that, we use a spectrogoniometer, which is located for now at EPAC in France. And we measure meteorite, basically putting light on the sample, measuring everything that's reflected back to have a reflectance spectra. From the spectra, we can get information very detailed on the mineralogy, on the composition of the meteorite, basically having a detailed information about this piece of space rock. So for the Hera mission, I used samples that were ordinary chondrite mostly, because those are silicate-rich meteorites. So not to go into detail, but we used HL and LL chondrite, which are different content in iron. And type 3 to type 6 is interesting because they have thermal metamorphism and different degrees of it. So type 3 have low thermal metamorphism, so low degree of thermal alteration. Type 6 have high degree of thermal metamorphism, so high degree of thermal modification. I also added, as you can see, a couple of other meteorites, so eucrite, acapulcoite. Those are just to be as thorough as possible with the study and be sure not to miss anything, only focusing on samples that we kind of expected to work. So how do we compare asteroid and meteorite spectra? I'll go very fast on this because this is just technical speaking, but just to show you quickly how we do it. The first one is a physical comparison, basically putting one spectra on top of the other and see if they match. This is for Didymos and 2 meteorite examples that matched quite well. This is a good matching. But we also did it for all the other S-type asteroids, all the S-type family, basically, to understand this family as well as possible in the Hera mission contest. So try to understand the composition of all the S-type family asteroids, not only Didymos, but the entire family. Then we did a parameter comparison. This is more a geometrical comparison of the spectra using the absorption bands. So we use the position of the slope, the depth of the slope, and also the depth of the absorption band, position, depth, and slope of the absorption bands. Not to show you all the details, of course, we use all those parameters, compare asteroids and meteorites together, and see the most recurrent match for all parameters. This is the result that we got at the end of this whole comparison study. For Dimorphos, it matched the best with an LL6 chondrite, meaning low iron content, but high degree of thermal modification, which was quite interesting to discover for Dimorphos asteroid. And for the whole S-type family asteroids, we found different matching, which was quite surprising. We had LL3 to LL6, but also L6 and Acapulcoite, which are all quite different meteorites. And therefore, we had one of the hypotheses is that the surface of those asteroids are not homogeneous at all. So there is a mixture of all of those meteorites at the surface of those asteroids. So this is one of the hypotheses. And for the thermal metamorphism, one of the main hypotheses for the asteroid is the onion shell theory, with a high degree of thermal modification at the center and a lower thermal modification at the border. So this showed us basically for Hera that Dimorphos and Didymos could not be very homogeneous surfaces, but could be a mixture of many different meteorites. We chose one main one, the LL6, but we added a couple of the other ones for the mission. Now, just to tell you a little bit of what's next, we know how to make the matching between meteorite and asteroid, but I have still a lot of work to do. First of all, for now, we use mostly grouped meteorites for doing the matching, so meteorites that are grouped already. But there are a lot of ungrouped meteorites and micrometeorites as well that I work a lot on that are not used yet in the matching. And those could help us understand much better the composition of the surfaces of the asteroid if we could actually use those as well in the matching. We could also use more than just powdered samples. For now, all matching between meteorite and asteroids are done on powdered sample, mimicking a regolith kind of fine-grained powder. But as we can see on some asteroids at least, the surfaces are not made of very fine regolith, but more boulder kind of surfaces. And in one of my previous studies, we saw that raw meteorite samples have very different spectra than powdered samples, and those could also help us understand much better the composition of asteroid surfaces. And finally, secondary processes. For now, all matching are done on powdered room temperature samples, but temperature can change the spectra, and also solar irradiation could change the spectra, and water content as well. So those should also be included in further studies to understand much better surfaces, have better matching between meteorites and asteroids to understand those compositions much more precisely. So one of my final points is to explain to you a little bit, so then we know which meteorite comes from which asteroid. What is it so useful for space missions? So for the Hera mission, they came to me to ask those samples, so I gave them the LL6 and some other meteorites. First of all, to calibrate the instruments. So they used those samples to calibrate the instrument on something, a material that is very close to what the instruments are actually going to measure once in space. So they used those samples to calibrate as well as possible before actually launching the instruments in space. But also now, during the mission, those samples are actually very useful to understand the data that have been measured by the Hera spacecraft, or will be measured by the Hera spacecraft, because those meteorite samples we can measure again and again and again, whereas compared to a space mission, we cannot do measurements as much as we will. But the meteorites are available in our lab. We can remeasure them, compare them to the data measured by the spacecraft, and thus understand the data at higher resolution and much faster in terms of efficiency. And my final point is, I hope I got you a little bit excited on meteorites, and also knowing all the different variability of material that we have in our labs already can help us choose next target for future space missions, or where to land, or actually which asteroids to go to, because we have samples already in our lab. So we could use them, and we should use them as much as possible to choose targets for future space mission. And also for space resources, we can use meteorites and what's in there. We know them, we can characterize them a lot. So I hope I got you convinced that meteorites are actually the next goal and something that we should use for future space missions. Thank you so much.
Thank you very much, Lisa. Other questions? Yes.
Hi, I'm Daphne Stam. I'm a planetary scientist from Leiden University.
Yeah.
So you do observations of the asteroids with VLT, and the asteroids rotate. You don't resolve them spatially. So do you see any variation in their spectra if they are inhomogeneous?
So there are the spectra that I showed, for example, for Dimorphos and Didymos, are an average of many, many spectra measured during rotation, during also moving and everything of the asteroids. Sometimes there are many measurements averaged in one, which is also why I think meteorite studies are such importance, because we work on an average spectra for full asteroids of many, many meters. So I think it's important to take this into account, that multiple meteorites are probably useful for understanding of full asteroids spectra.
Yeah, and could you also then not analyze measurements with a higher temporal resolution?
This is the goal. I haven't done it yet, to be honest, but I would really like to have more time to actually do this and see if we see a difference. That would be super interesting.
Okay, thanks.
Yeah.
Matthias, please.
Hello.
Hello,
Matthias
thank you.
Sperl, Cologne, Germany. When you were referring to the powdered spectra being different from the raw spectra,
Yes.
does the correlation between the grains play a role, or what is the reason for those deviations?
So this is something I'm looking into right now. What I can say for now is that this difference is not exactly the same for all material. So there is, of course, a link with material and grain size that you can get. I think it's especially visible for silicate material. We see it much less for carbonaceous-rich material. So I think, of course, it's influenced by material, and I think silicates is even more important for this difference that we see.
Thank you.
Thank you.
There's another question over there.
Hi, Lisa, nice presentation. Ciprian Popa
Thank you.
from Naples, Italy, National Institute of Astrophysics. What kind of resources are you planning to target on these asteroids?
Oh, this is probably not a question for me. I think asteroids are something in the long, long run and a long idea. I think people have been presenting lunar samples, and I can, from this week, see how difficult it already is. In terms of which resources, I think if you look at the previous presentation presenting rare earth elements or PGE elements, platinum group elements, are extremely rich in chondrites and meteorites. So those would be, I think, the main target for resources on asteroid, but I think this is in a much long-term type of goal. Thank you.
Thank you, Lisa.
Thank you.
So, up next is Pavel Porizka. I hope I did this right. So, and he's going to talk about his topic of laser-induced breakdown spectroscopy.
Okay, thank you, Dennis, for a very kind introduction, and I'm really happy to be here. And I will be presenting something about LIBS. And you might know LIBS already, or you will learn more about it in my presentation. I'm sorry that I don't have the template, but that's life. Yeah, so what I will be talking about is that what we are doing at CETEC, at the Brno University of Technology in Czech Republic. Basically, I will be targeting three main topics, which is first the development of a payload that we also aim for terrestrial operation for some drones or rovers, and you can see some demo that we did recently, and we will be continuing on it. So you can see the black box in the middle with orange logo on a military-grade rover that we did together with our colleagues from another faculty. If you're interested in the development and the stuff that we do for LIBS system, also please feel free to ask, or I will just also forward your questions also to Ina Uverova, who is with us, and you might know her as well. So she is behind the development, but unfortunately she couldn't be here today. Also, I will be talking more about how to use LIBS. Actually, the qualification of LIBS will not be just about what we do with the system per se, but how we can use LIPS, because using LIPS in lunar or Martian environment is actually limiting based on the atmosphere that is present, and yeah, we'll see what's actually happening. And then also how to do the system calibration, because it's necessary prior to any mission. So you know LIPS, if you know the mission, so there is a Chandrayaan, it carried LIPS payload already. There were two missions proposed by DLR in Berlin. So this is the LUVMI-X and light rover unit, which is down below, and also two missions which are proposed by our team. First is the lunar LIPS that I will be showing, and then also the other one, which is from our colleagues also in Prague, which is combining not just LIPS, but also Orbitrap mass spectrometer, which is really interesting technology and nice combination. But before you can do some LIPS deployment on the moon, you have to really go through a lot of stuff. And this means like to start from the basics in the beginning, to just understand LIPS in this environment, which is really strictly limiting the performance of LIPS, basically by even just like creating plasma under vacuum. That's a really significant burden, basically, that we have to target and think about. And then also do some, like, to understand the geology, and this is, we are doing this with Dennis Harries here in Luxembourg. We have a joint project. Soon, Dennis also should have some system from Brno, basically also to provide LIPS and LIPS under vacuum conditions. So we will be happy to also share some information together on this aspect. And also when you just understand the geology, you can move towards the system development. But here you just like hit the wall because there are not so many lasers commercially available. So you need to treat this, also spectrometers, and also like the whole system. And then you have to put it on some carrier, on some rover, and we are targeting some partners in this. I'm not listing everyone, so I'm sorry if someone is missing here and feels like should be there. So basically, I will just like mention what we do with the system development very briefly, because it might seem that like developing LIPS payload is very easy. You just take LIPS, you just take laser, pulse laser, you put it with a lens over the sample, you just put a pulse on the sample surface, create the plasma, and that's it. You just collect the radiation. But it's a bit more complicated than that. You just need to have the geometry. You just need to really do some like trade-offs in the optomechanical design, and this really starts to get interesting. Also, we are having the laser development that we are targeting with a partner from Lithuania, and this might be an ESA project that will be like space-grade laser that would be reusable really directly for lunar LIPS applications, which is really promising for us, and really one thing that we really need to have. I'm sorry, but I will just like briefly mention what is LIPS and how LIPS works actually. So as I said, you just deliver a laser pulse to the sample surface, you ablate the material, create a plasma, and this plasma radiates to all directions. Basically, it's like a small flame, and it contains the elements from the sample, and then you collect radiation. It's very simple, straightforward. That's why many people just like run into it. But then when you start working on it, it has some drawbacks in some matrix effects and so on, and the calibration and interpretation of data is not so straightforward, but we have tools to do that. As I mentioned, when you just go for like terrestrial application, you have very nice ambient atmosphere that confines plasma on the spot where it was created, and the plasma is really dense, hot, and then also has really nice analytical performance. But when you go to the Mars, where there are a lot of systems already, like to NASA, one Chinese system that is using LIPS, you see that with slightly lower atmosphere, you just get bigger plasma. The plasma doesn't feel that confinement, and you are losing sensitivity. So you have to really treat that properly. Despite that, all those rovers on Mars can do it like standoff detection. LIPS is really powerful in that you don't have to come to the sample, you don't have to reach it directly with a contact, but you can be distant in several meters, up to several meters. But then I'm just showing that this is like 10 to the power of -7. This is not the real moon vacuum, but like from the vacuum theory, you don't have to go deeper, because then it doesn't matter if you go deeper with vacuum, because the plasma will be spreading super fast regardless of the vacuum, because it doesn't feel any confinement. So there the plasma has a really long lifetime, has a low temperature, and then you're losing sensitivity. And this is what will be very limiting factor for LIPS on the moon. Despite that, LIPS was deployed on the moon. There was already some spectra, and it was quite nice. So you can see what happens also to spectra. Maybe you see that, I'm sorry, but you can imagine that just like the spectra are getting less broadened, but also less intense. So there is a trade-off that you have to treat and you have to keep in mind. So on lunar payloads, we will be very close to the sample surface, which is very important. I will be just showing what we do with data and how we calibrate our systems. So basically, any analytical chemist here sitting knows how to calibrate a system, how to do like the intensity as a function of content. So this is very obvious and straightforward. But what is necessary is also do like the automated mineralogy, what you can see on the right side, and also quantitative elemental imaging. So this is the typical result that you can get from LIPS, that you can have really high throughput analysis in terrestrial conditions very easy, and you can do large-scale imaging of the sample surface and see the distribution of elements within the sample. And this is really crucial, and you can just really boost geological analysis with LIPS, and this is very promising. And we cooperate with many geologists providing large-scale maps and images showing the distribution also of light elements like lithium, beryllium, or other elements. That's why also LIPS was suggested for hydrogen and volatile detection. Yeah, so LIPS is in this particular aspect, LIPS is very powerful. And then this is like my favorite project here left on the bottom is how to just like connect systems through what we are now starting to use foundation models, how to just like use data from each system and transfer them between systems. Yeah, so I will just show one thing that we did here with Dennis Harries and my former student Daniel Holub. So this is actually imaging of lunar meteorite with large-scale imaging with fine resolution. You get a lot of data that you can process, and based on strategy or with like a reference method, we were able to calibrate the system that we can see actually quantitative elemental images of the meteorite. So this is very promising further step. On the previous slide that I skipped, you could see the automated mineralogy that we can really calibrate the system to see individual minerals, not just elements. So this is important for the geologist. And the last step that we do also transfer data from one system to the other. We already have publications on this, and now we are moving this into like calibration of our payloads. I don't have time to speak about everything here, so I just like let me quickly summarize. So we are developing the system for rovers and drones. We would like to also do some upstream and delta development for the lunar LIPS payloads. Hopefully we will be funded also here, and then the data mining with automated mineralogy and library transfer. So this is very important, and thank you for your attention.
Thank you very much, Pavel. Other questions? Yes, please.
Hi, Pavel. Nice presentation. Ciprian Popa from Naples, Italy, National Institute of Astrophysics. How is this system behaving in the presence of iron? That would be the first one. Yeah. And how is the system behaving with the reflective minerals, like the opaques?
Okay, so iron we can detect quite nicely. The drawback I don't want to say drawback, but iron has many lines, so you can just really select. We can also calculate temperature based on this. So iron is nice, but you have to know what lines to select. Obviously, we can do that. So you can also calculate the temperature, do some calibration-free analysis, even with this, and so on, so on. So iron, like magnetite and some other minerals we are trying to use, and then to see how lips can do some performance with some reflectance. We treat the sample. We just like really to polish it first for like lab-based analysis for the imaging. Otherwise, we need to look into that. I don't have direct answer for the second question.
Just a small follow-up on this one. So can you detect, for example, like smaller concentration minerals or elements in the presence of iron? That was the real question.
Yes, you need to know where to look for the particular element. We are trying to also do some like artificial spectra creation, so you can see really how the lines are getting to each other, if there are some interferences in spectral line. And with a shell spectrometer, you can have really nice resolution, so you can really get those lines apart. But this is where you can talk about it. This is really nice stuff that I have some answers to that in more details. Yeah.
Franz, please.
Yeah, thank you. Franz Renz, Leibniz University, Hanover. It's a very nice device. What is the minimum weight you can achieve? We know the Perseverance, it's several kilograms, but they also have a long distance, several meters. So what is your longest distance and minimum weight? Oh,
the longest distance minimum weight is like 3 kilos. And this is like the small payload is like really carryable, and the distance is like 25 centimeters. Yeah, we don't go further because then you are losing sensitivity. You have to have small optics and so on. So this is like trade-off. Yeah.
There was another question, please.
Thank you, Fernando Pedichini from Italian National Institute for Astrophysics. Maybe I missed it during your presentation. What is the wavelength of your laser?
Yeah, we are using fundamental wavelength of Nd:YAG. This is 1064 nanometers. We can also use longer. We tried also 2.2 microns, which is also working. It's eye safe, so it's better for the rovers, terrestrial and drones. Also, you can go to UV range with 266. It's like geology is not so demanding on the laser matter interactions as like soft and hard tissues that we also do.
Okay, thank you.
Thank you very much, Pavel.
Yeah, thank you very much.
So we move on to the next speaker, which is Stephanie Halwa, and she's going to talk about noble gases in Apollo 16 regolith samples.
Thank you. So I'm going to be presenting some of the work that I did as part of my PhD at the University of Manchester, which is Apollo 16 regolith noble gas inventory as an analogue for the lunar South Polar region. So for those of you that don't know a lot about noble gases are a group of inert elements that are in the gaseous phase on Earth. And because of these properties, they're really useful tracers for volatile delivery and surface processes. So they can trace processes that affect hydrogen and water, which is much more reactive and harder to understand. The noble gases can also be used to test how representative samples are from a chemical perspective, and they're also directly relevant for resource use and moon operations. So I'm sure the big thing at the moment is helium-3, which is a noble gas, obviously for fusion fuel, but also xenon is used for rocket fuel propellant. And so in the lunar regolith, the noble gases have three main sources. We have in purple the solar wind, which is a stream of ions that comes from coronal mass ejection events from the sun, and they implant on the surface of grains in the less than 1 centimeter regolith depths. Secondly, we also have cosmic rays in red, and so these come from both the sun and intergalactic space, and they interact with certain elements in the rock to produce cosmogenic nuclides, which you can see in the bottom right. And lastly, we also have impactors. So these are comets, asteroids, and micrometeorites, which bring exogenous volatiles in. And these also fragment and mix the regolith, redistributing the volatiles up to depths of several meters. And you might be wondering, right, we're at a resources conference. Why do we care about the sources? It's a very scientific question. But actually understanding the sources of these volatiles has really big implications for the sustainability of resources. So for example, if the volatiles that we're looking at are from the solar wind, that proves more of a sustainable resource use, whereas if they're from impactors, the flux is a lot lower and it's a lot harder to be able to prospect them in a sustainable way. So as you know, there's lots of upcoming missions to the lunar south polar region. I've just got a Diviner annual maximum temperature profile here showing these PSRs that might have enhanced volatile concentrations with the green dots. And one of the missions that I'm involved with is ESA's prospect package. We've actually have a model just sort of in the corner in the other room, so please do take a look, and if you have any questions, I'll try my best to answer them. But Prospect is going to go to the South Polar region on an Intuitive Machines lander at the end of 2027, and it will do in situ ground truth measurements of the abundance and isotopic composition of volatiles, including the noble gases. And as you can see, it has a drill on it, so it will drill up to 1 meter's depth below the regolith surface to collect both surface and subsurface samples. And in preparation for the mission, the landing site for Prospect is likely to be a very heavily impacted highland terrain, and the best analog samples we have for that are those returned by Apollo 16. So what we really want to do is understand what the ice-free regolith volatile budget is to use as a dry baseline to compare with potentially wet samples. So Apollo 16 was the only crewed mission to visit the central near-side lunar highlands, and you can see its location circled here. And we've chosen to look at double drive tubes, which sample up to 60 centimeters depth below the lunar surface, and these provide the best depth comparison with Prospect. And I've highlighted some of the samples that we've got here. So we looked at 2 double drive tubes that were taken 50 meters apart. And we hope that these kind of represent end members of what we might expect in the South Polar region. And then we also looked at 1 sample from the Station 10 core, which had a exotic high titanium Mare basalt classed in to look at the effects of exotic material. So we analysed noble gases using a noble gas magnetic sector mass spectrometer, much like the one that will be on Prospect. We used 5 milligram subsplits, which were the gas was liberated by heating using a diode laser, and we used 4 heating increments with laser powers ranging from 0.01 to 21 watts, which is around 600 to 1300 degrees. And just to compare this with the mission, on Prospect, we're actually heating the samples using ovens, and these only reach 1,000 degrees Celsius. And we saw complete melting in our 3rd temperature step, so we probably won't get a sample melting on Prospect, but we can look at the sort of gases that we will get in the low temperature steps. So here I have the total gas inventory split by the steps for the 11 samples that we looked at. And in blue is the very lowest temperature step. And you see that actually most of the noble gas budget is liberated by these lower temperature steps. And only like less than 5% is liberated in the highest temperature step. And so we can look at the isotopic composition of the noble gases that are released in order to understand what the sources are, and we do something called isotopic deconvolution, which if you want to learn more, you can ask me. But we see that lowest temperature step is dominated by solar wind signature, and actually this really low release high temperature step has a little bit of cosmogenic in, which is contained in the mineral lattices. And this is also higher in the samples from deeper in the core. So if we look at the noble gas abundances with depth, I've just chosen 1 isotope for all 5 noble gas species, but what you can see is it aligns with the literature data, which is great. It varies systematically with depth, and the species co-vary with depth, which is what you can see on the plot here. And we see that, for example, helium-3 ranges from about 1 to 15 times 10 to the minus 6 cubic centimeters per gram of regolith, whereas 132 xenon, for example, is about 3 orders of magnitude lower than this. And what I'd really like to draw your attention to is actually the green points. So these were repeats that we conducted on the same subsplit, and you actually see the concentration of noble gases varies by quite a lot. And this has really important implications because we see heterogeneities on a milligram scale, which means we have to be really cautious when we interpret profiles. But nevertheless, there is some kind of stratigraphic correlation going on. So I'll take you through this step by step. In the first pane, we have 36 argon, which is used as a proxy for solar wind abundance. And we see there's a layer highlighted between 50 and 60 centimeters depth, which is really low in this 36 argon, so doesn't contain much solar wind. In the second panel, we have neon 21, which is used as a proxy for cosmogenic abundance, and we see this is actually consistent with depth. And what's quite interesting is if we compare these two plots with panel 3, which is the regolith maturity, I think Clive touched upon it earlier, but it's actually slightly disconnected from the maturity for both of the cores, which is quite interesting. It shows noble gases don't actually follow a predictable gradient with depth. And so then if we move on to the fourth panel, this is comparing the relative retentivity of neon to argon, and we see the retentivity is actually highest in this sample that's from the 50 to 60 centimeters depth. And what this means is combined with the low solar wind abundance, it didn't have a very long surface exposure, it didn't get exposed to diurnal temperature variations, which lead to diffusive degassing and the loss of the lighter isotopes like helium in neon. And you can see that actually the overlying samples have been affected by this process, and so therefore we can restructure some of the core stratigraphy from the noble gas data. So just some implications for polar volatile exploration. The Apollo 16 volatiles do not follow a predictable depth gradient, and they're also heterogeneous on the milligram scales. And this has important implications because single analysis of samples may under or overestimate resources that are available. And it means we actually need to go and get a really big data set to really understand what resources are available to us at the South Pole. Volatile signatures are overprinted by surface processes, so this includes the diffusive degassing by diurnal temperature variations, which can lead to loss of light species, and this would affect like helium and water as well as neon. Volatiles in the expected wet polar regolith that will be sampled, hopefully by Prospect, will likely face the same complexities as the Apollo 16 ones with the added component of the cold trap. So it's going to be a very complicated isotopic problem for us to untangle. So in summary, the dry highland noble gas inventories are dominated by the solar wind, which is more of a sustainable resource than if it was from asteroidal material. And they also have a small cosmogenic component. The majority of the light species are released at low temperatures without the need for sample melting. The upper regolith is significantly processed and reworked through impact gardening. This will complicate the interpretation of polar regolith volatiles, and then you have the added component of the potential cold trap volatiles. And so Prospect will sample the volatiles that were released at the low temperature steps in this study, and this will likely be mostly solar wind dominated unless the potential cold trap component is large and not overprinted by the solar wind. And I've recently changed affiliation, so I've got my new email address at the Open University there. But thank you for listening.
Thank you, Stephanie. Other questions? Clive, of course.
That was a very nice talk, Stephanie. Clive Neal, University of Notre Dame. Have you thought about the Apollo 16 deep drill core? You're only doing push cores with those.
Yeah, so the deep drill core went down to 2 meters, so it's, able to sample the same. Unfortunately, in the CAPTEM request that we put in, we weren't able to get deep drill core samples. But it would be pretty cool to look at. I don't really have the time to look at it at the moment. We've started looking at some new samples, and sort of the next step is we're going to mix in some meteorites with the Apollo soils to see what the asteroidal component would look like if it were to be present.
Okay. There may be some literature data that would be useful for you.
Yeah, I actually, on the plot with the abundance with depth, I had some of Don Bogard's data there where he did the deep drill core, and he also did the same core that we did, so we wanted to use that as like a ground truth comparison that we're definitely measuring the right thing.
Jakub, please.
Thank you, Jakub Ciążela, Polish Academy of Sciences. So we are stick to helium-3. Argon seems to be quite a good proxy, maybe even better than optical maturity. Have you tried to correlate helium-3 with argon? Can you make some analysis of both volatiles in one sample, in a set of samples?
Yeah, so all the samples have complementary full suite noble gas analysis. So all the noble gases were collected from the same sample. So the argon that is presented was released at the same time as the helium. And there is some correlation between helium-3 and argon-36 because naturally they're both sourced from the solar wind. So they're going to follow the sort of solar wind ratio. But at the same time, we do see a lot of helium-3 loss in the samples because of the diurnal temperature cycling. So it's not quite, it's on something that we call the implantation fractionated solar wind, and it's kind of hard to tell if it's because the solar wind is getting fractionated as it's implanted, or if the helium-3 is being lost through the heating. So I hope that kind of answers your question. But we can talk a bit more later if you want to know more. Yeah.
It's very interesting, thank you.
Cool, thank you.
Any other questions? We still have some time. Okay, then thank you very much, Stephanie. And we move on now away from actual measurements and sample data to data sharing. And I welcome to the stage Antonino Salmeri.
All right, just confirming you can hear me. So I realized not only I'm a, whoa, perfect. I already broke something. So not only I'm a lawyer in a prospecting session, I'm also the last speaker before lunch. So I realize I have a big responsibility here. I'll try my best to be concise and also entertain you to talk about information sharing for space resource prospecting. All right, so the basics, I think, have already been established throughout this whole session, and I would say over the past years in this conference. We definitely need more data and information to estimate whether there are reserves on the moon. I think we are also pretty clear at this point that to collect this data, we need a lunar prospecting campaign, as you might have heard a few times from some people at this event in the past years. The question then becomes that we also need policies to manage both the process of collecting information and data and also what are we going to do with the data once it has been developed. These policies are there, as we, I think, have been saying over the past couple of days, for those of you who were at the legal session yesterday, they are there to enable these processes, not to restrict them, not to constrain them or block them. They are there actually to make them work. We need, in fact, to streamline and synergize the collection process for efficiency. We need to collect the same information, and we need to have policies that help us understand what do we want to collect and why. We need also streamlining so that we can compare and then integrate and combine the data so that we can actually have higher impact with the data we're collecting. And finally, we need policies to validate and certify the data that we are collecting so that we can utilize them for estimation of reserves. This is also what happens on Earth, where prospecting is done in accordance with codes, industry standards, and regulation so that it actually delivers the result that it's supposed to deliver. And here comes the law. And of course, the lawyer. What is the law role in this? It, first of all, provides certainty, right? What are your rights and what are your obligations as you engage in prospecting activities, particularly on the side of information sharing? The law is also there, and I want to emphasize that, to protect interest, especially commercial interest, but also the public interest. The interest in getting information which is truthful, verified, and reliable. And finally, through these functions, the law will enable progress through this certainty, through protection of interest, then we can really go and have peace, safety, and sustainability on the moon. Very quickly, for those of you who were not at the legal session yesterday, what is space law? A little crash course on space law. Space law is a multi-level system. It is combined between international agreements concluded at the United Nations over 50 years ago that form the Corpus Juris Spatialis, or international space law, and then a series of domestic legislation. You heard that from Rosanna a couple of times at this point, which interpret and implement the obligations that exist at the international level. I would encourage you to think about space law as a dynamic system. It's not rigid. The treaties have been there for a long time now, but they are general, they are principle-based, and they are implemented and interpreted through domestic legislation over time. And space mining is, in fact, the best example of this dynamic evolution of space law. Through the evolution of space law, we arrived to space policy. And just like space law, space policy is also a multi-layer process. It works at the United Nations, where there are all states united at the UN Committee on the Peaceful Use of Outer Space, with the support of the UN Office for Outer Space Affairs. It goes to the minilateral level. Well, some states come together because they have a project, because they have a shared interest, because they have shared values. This is the example of the Artemis Accords and the International Lunar Research Station. And then it's multi-stakeholder. It's all the others who are not state, so-called non-governmental actors, private sector, NGOs, experts, such as we do at LPP, such as in this very country started the Hague Working Group, which created the building blocks on space resources. Now let's take a look very quickly at what are the foundational principles from the Outer Space Treaty that are relevant in this case to space, to information sharing for space resource prospecting. So I'm not going to touch upon the legality of space mining. We discussed that in other times, and colleagues have talked about it yesterday. What I will point your attention is that there is already a provision in Article 11 of the Outer Space Treaty that says that states agree to share information on the nature, conduct, location, and results of their activities in outer space. This is already a legal obligation. And how does it work? It works through a process that happens at the diplomatic level at the UN. So a state sends what is called a note verbal, which is a diplomatic communication to the UN Secretary General, in this case to UNUSA, and that goes uploaded to an index of submission from member states under Article 11. This is publicly available on the internet, and you can consult it. And for your awareness, lunar activities were the very first submission in 1967 when the Surveyor mission was made by the United States. Information on the result of that mission were shared under Article 11. And they are also the latest information that have been shared more recently. 2025, Luxembourg shared information on the iSpace mission that was supposed to extract and collect resources on the moon. So there is already state practice, consistent state practice on using Article 11 for information sharing on lunar activities. Then we go to the national level. As you know, there are 6 countries in the world that have adopted frameworks on space mining. Some of them have legislation, like the United States or Luxembourg. Some have just policies, like India. Some others have a complex framework, like Japan. And some others have just beginning to address it, like Brazil and UAE. What matters in national framework is how they get implemented in licensing. So through national frameworks, we create licensing systems. When you get a license, then this license is also published, because governments, at least in the countries that we are examining, in this case, Japan and Luxembourg, they have an obligation for transparency. This is in the law of space resources of Japan, and it's also, generally speaking, in the law of Luxembourg. So you can find online on the register of the Cabinet Office of Japan and the Ministry of Economy in Luxembourg and the LSA an announcement of who got a license to explore and eventually collect and utilize resources. And in Japan, which goes one step further, you also have a detailed business plan that needs to be shared so that the activity can be coordinated with others. So they are already thinking about that coordination aspect that could also be relevant for prospecting. So again, there is also domestic state practice in policy for information sharing. And then there is multi-stakeholder information sharing. Now, of course, I can only speak for my organization. Last year, we spent 9 months working on a document called Lunar Information Sharing 101, which is a part of other type of policies that we have developed with LPP throughout the years. Now, more specifically, for 9 months, we interviewed over 45 stakeholders, including governments, space agencies, companies, research institutions, universities, even ESRIC, on the core elements, principles, and practices for lunar information sharing. Specifically, we look at the why, what, where, when, and how. And the goal of the document, which is publicly available online, you can find it on our website, you can download it. If you were lucky last year, I might have given you a printed copy. Maybe we'll do a second printing this year. The goal is to support the development of policies at the multilateral and domestic level. So in the final part of the presentation, I will give you a quick overview of what are the core elements of lunar information sharing that we have identified from the research that we have done last year on the Lunar Information Sharing 101. Starting with the why. Why do we share information? Why is it beneficial? What's in it for me? In the consultations that we did, we identified 4 key purposes, including ranking them in order of priority. So the number 1 priority is safety. We share information because we don't want to bump into each other. We don't want orbital collision. We don't want surface interference. But we can also share information for peace, to showcase to the world that what we're doing is lawful, that we have nothing to hide, that we're not doing any sketchy activity on the moon. And then we can share for sustainability and cooperation. Lesson learned from things that have gone wrong on the moon will be extremely helpful to improve our ability to operate long-term. And we also want to make sure that we can explore together through international cooperation. So by sharing information, we bring together different stakeholders on shared projects. What to share depends on the why. So we have developed a matrix that you can find here, and then the document elaborates more about it, on what are the core elements that you need to share if you want to achieve a certain purpose. You'll see that safety is the one that requires the most information, because of course there is a number of details that needs to be shared to avoid the operational interference. But for peace or for sustainability or cooperation, we don't need to know everything, and certainly we don't need to know protected information by intellectual property rights or national security. What we're talking about here, what you see in this list, is pretty basic. It's just, what are you doing, who are you, when are you staying on the moon, how long are you staying, what are your intentions? Very, very basic things that will be public anyways. There is no point in hiding because the moon is under everybody's eye. If we share, though, we can use them for these purposes. Then the question is where to share. Where do we put and find the information? I already mentioned the Article 11 index. There is also a register of space objects when we're talking about sharing information on specific objects. And then there is the website of operators and also website of domestic authorities that host licensing for activities. Then we arrive at the how, which is probably one of the most trickiest questions. When we consulted with certain governments on information sharing under Article 11, they said that they didn't use much that provision because they didn't know how to share. And mostly they didn't know in which format to present the information and what information to include. So over the past 5 years, since 2021, we started a project on the development of a lunar template, which will be available, and it is in fact already available on our website, for anybody who wants to use it on a voluntary basis. And this is just to streamline the way we share and present the information. If we all follow the same approach, whatever that approach is, this is just one of many suggestions if you wish, then we will be able to compare and integrate the information and actually do something useful with them. Finally, but not less important, the timeline is crucial. When to share matters. Again, if you want to share information for safety to avoid accidents, you have to share in advance. If you share that information when the activity has already been done, it's too late. We cannot do anything about it. On the other hand, if you want to share information for cooperation, we are actually more interested in what you're going to discover during the mission. So we don't need much information before, but we would like to have some information after or during the mission. When we consulted with stakeholders about an approach for this, everybody noted that an incremental approach could be feasible and more adequate for lunar activities. So there are several checkpoints. You start 1 year before. Again, could be 2 years, could be 3 months. The question is, we need to agree on when do we want to share information for predictability, so that you know when the others will share, and you can expect to do the same in a consistent manner. So there are 3 checkpoints to incrementally share before the activity, and then 3 more checkpoints to share incrementally after the activity. And again, the reason that you share before or after depends on the purpose you want to achieve. So in conclusion, and noting that I am already a little bit over time, and sorry for that, Dennis, we need the data, we need the information, and we need law and policy to organize the collection of that information, validate it for the purposes of reserve estimation so that we can use them to then conduct space resource activities. We already have foundational work. What we need is just to tailor it specifically to the prospecting needs on the moon. And that's why I'm pleased to conclude by announcing a new project between ESRIC and LPP on information sharing for resource prospecting, which will hopefully start in the next couple of months. And it will be a pilot study on specific protocols and needs of information sharing for the purpose of resource prospecting that then can hopefully be shared with all of you so that we can have a common approach on how do we share information for prospecting resources on the moon. And with that, I will conclude, and thank you very much for your kind attention.
Thank you, Antonino. We have time for one quick question. Is there one? Ben, please.
Ben Buss, the Intuitive Machine. Could you talk a little more about your perspective on Article 11? Because there's a big difference here between publishing things to avoid conjunction events. But when you start to talk about publishing of science data as an obligation, then you're cancelling the possibility of a commercial company acquiring data that is only going to do it if they can make value from the data that they collect.
Yeah, thank you. I'll give you a lawyer answer, which is it depends, right? So Article 11 says that states agree to share information inter alia on the results of the activities. Now, I think the answer to your question is that you can share certain layers of information and data that do not undermine commercial interest, that it's general, that it's raw data, that is not processed, that it's just a description of the results that you have identified, and you can reserve more details that is under commercial proprietary rights for other types of information sharing. So don't see that as a black and white type of obligation. You either share everything or you share nothing. I do think, and working with member states, we are discussing that there is a middle ground where you can share some high-level information that are beneficial for everybody to comply with legal obligations and, again, to achieve certain purposes. And then you reserve the rest for legitimate commercial activities, as we've been doing anyways already on Earth. Much of the activities that are funded by governments are shared publicly, because this is a requirement that goes beyond space law. It's there in legislation, especially in the United States. So we need to find a middle ground, and I think it helps if we all understand that we want to protect commercial interests, but that doesn't mean that then we can do nothing.
Thank you very much, Antonino. I think that concludes this session. Thanks again to all the speakers and the technical team in the background. And in case, if you haven't done so, please go to the reception and vote for your favorite poster. Enjoy the lunchtime, please.